Thanks for the introduction. My name is Shutaro KARUBE from Kyoto University. So recently my affiliation was changed from Tohoku to Kyoto University, but this work was performed in Tohoku University. So thanks a lot for the co-authors, Professor Nitta and Professor Koda. Furthermore, I'd like to appreciate all of the organizers of the workshop for giving me this special opportunity. So I will tell you the experimental observation of the spin split effect and the application in altermagnetic ruthenium dioxide. As an introduction, so we know that MRAM is one of the most important devices in spintronics. So as for the operation principle, it's just a magnetization switching. This corresponds to the information rewriting. As for the common sense so far, that we should use external feed for the switching. But for more efficient control, how can we perform the switching? So Professor Liu in MIT answered, let's utilize the spin current in 2012. It's 10 years ago. So that we know the spin current is flow of the spin angular momentum without a net charge. So this current can affect the magnetization as a finite torque. So that this current can be easily generated via the spin Hall effect. But there was a problem, for example, in the platinum cobalt bilayer system, so via the spin Hall effect, we apply the charge current into the platinum layer, we can generate spin current, and then finally the spin of torque is affecting on the magnetization. But due to the orthogonal relationship among the spin current and the spin polarization and the applied charge current, the vectors, so we cannot perform the switching without magnetic field. We need external magnetic field for the breaking the switching symmetry. So after all, we need the external field for the switching. So the Nobel spin current generation technique is quite desired so far. So based on this background, how can we newly generate the spin current in the magnetic family below? So as for the non-magnets, as I mentioned before, so for example, the heavy metals such as the platinum and tantalum or the semiconducting gallium arsenide, so due to the breaking parity symmetry, we can get a spin splitting state on the electronic bond structure, and finally we can get the spin current via the intrinsic spin Hall and the Dirichlet effect. As for the ferromagnets, this is just the information carrier which has a magnetization, we know, but this material also can generate a spin current. So due to the breaking time reversal symmetry, we can obtain the spin polarized and the pure spin currents via the anomalous Hall and the spin anomalous Hall effect. On the other hand, as for the conventional antiferromagnet, such as the nickel oxide, there is a preservation of the parity and time reversal symmetry leading to the spin degeneracy. So maybe we cannot get a spin polarized spin current. But the breaking time reversal symmetry maybe has a key to find a novel way to generate the spin current. So let's focus on this kind of the magnet. So as for the ferromagnetic origin, so there is a spin anomalous Hall effect. So this effect originating from the collaboration with the two phenomena, such as the ferromagnetic order and the spin-orbit coupling. So as a result, we can get a magnetization-dependent spin current, as shown here. So importantly, in this effect, we are now free from the orthogonal relationship like spin Hall effect. So we have a possibility to perform the field-free switching. The DC effect was theoretically predicted in the 2015. After that, there are several experimental reports of the effect in the amorphous cobalt iron boron and L1GO ordered iron platinum alloys. So this is a novel spin current generation with a breaking time reversal symmetry. As for the antiferromagnetic origin, So there was a really interesting report regarding the observation of the antiferromagnetic spin Hall effect from the Chenson's groups. So in the Corinian antiferromagnetic manganese gold structure as shown here. So in this material, due to the breaking parity symmetry, like a Dressel house spin-orbit coupling, so the up and down magnetic moment with antiferromagnetically coupling feel the different spin-orbit field due to the Dressel house type spin-orbit coupling. Then finally, we can get unconventional spin, polarized spin current. So importantly, that this polarization, such as the Z or the X type of the spin polarization, is perpendicular to the Nell vector as shown here. It's product from the spin orbit field. So that they also reported the field free switching using the this antiferromagnetic spin Hall effect as shown here. So this is also the collaboration with the two phenomena. Such as antiferromagnetic order and the spin orbit coupling, they lead to the spin splitting on the electronic band structure. Then finally, we can get the unconventional spin current and the field free switching. Up to this slide, we employ the spin orbit coupling to generate unconventional spin current. So here the question arises naively. So is it possible to generate the spin current without the spin orbit coupling from only magnetic order? So the Hiro-Shinobu and the Thomas Jungas groups theoretically predicted that the spin degeneracy should be resolved by using the crystal field, anisotropic crystal field, even if in antiferromagnet. So this feature is recently called altermagnetism, we know. So let's focus on this magnetism. For doing it, so first of all, let's remember the conventional antiferromagnet, as I mentioned before, in the nickel oxide. So this oxide has a high crystal symmetry because this oxide has a rock salt structure. So therefore, there is a preservation of the parity and time reversal symmetry leading to the spin degeneracy, so that we cannot get the pure spin current from this type of the oxide. On the other hand, altermagnet, so up and down magnetic moments in the different crystal field with anisotropic crystal field with antiferromagnetic coupling has a different band structure. So in this case, we can break the parity and the time reversal symmetries. According to the previous discussion, maybe the breaking parity symmetry for the altermagnetism is not important, but in this case, there should be the parity and the time reversal symmetry breaking. So this leads to the spin splitting, even though without the spin orbit coupling. So based on this magnetism, we should get spin current generation, especially this spin current depend on the Nell vector in the antiferromagnet. So the theoretician also reported this unconventional spin current generation in the Beard altermagnetism. It's called the spin split effect recently. So based on this report, we are very interested in the spin current generation using the altermagnet. So what material has altermagnetism and the high electroconductivity to generate unconventional spin current? So we know that for the spin current generation, we have to apply the charge current, so that we need a high electron conductivity material for the study. So actually, it was just ruthenium oxides. Many presenters emphasize the ruthenium oxides is important for the altermagnetism. So we will also focus on the ruthenium oxide. So before that, there are the similar origin. It's a magnetic spin Hall effect. There was a report observation in the manganese tin wires and metal. the authors found the magnetic order dependent spin accumulation or the spin current generation in the material. Furthermore, our group also found anisotropic X-polarized spin current in the manganese platinum alloys, originating from the spin momentum locking from the non-collinear magnetic order. So this is also a novel spin current generation with breaking time reversal symmetry. And so this is kind of the family of the maybe the altermagnetism. So here let's focus on the altermagnetic ruthenium oxide. So this oxide has a lucidum structure, we know, and further the metallic resistivity around 100 micron centimeter, and the null vector direction is a 001 or the 001 bar direction. So this oxide was found to be an antiferromagnet in the 2017, surprisingly, by means of the neutron scattering experiment. So actually this oxide can be easily prepared by RF magnetron sputtering. So after the preparation, we confirm the crystallinity using the XRD, conventional XRD, and the TEM and the XPS. Then found that we successfully prepared epitaxial ruthenium oxide. Furthermore, we also prepared several crystal planes, such as the 101, the 100, and the 001 films. So using the prepared films, we further fabricate a waveguide device to perform the spin-torque ferromagnetic resonance STFMR. So as shown here, this is just an experimental setup and a schematic image. So we employ the permalloy as a spin detector in this measurement. So this is a STFMR signal as a function of the applied magnetic field. We know that we can divide Lorentzian and its derivative. Using the amplitudes, we can analyze the spin current generation in the material. So here we found asymmetric amplitudes between at the positive and the negative resonance field. So this is curious when we focused on the conventional spin Hall effect. So this result, the implies is there is unconventional spin polarization of the generated spin current. So for more detail, we proceeded in plane field angular dependence. So this is just a result for the symmetric and asymmetric amplitude as a function of the phi h. The phi h is defined as a relative angle between the upright current direction and upright current direction and the external field direction. So using this kind of sinusoidal function, we can distinguish x, y, and z polarized spin components. So then we found the unconventional signals regarding the z and the x polarized spin currents. This cannot be appeared in the conventional spin Hall effect, we know. Then of course, we also try to investigate the kappa insertion case, as shown here, that then found the similar results. So we concluded the exchange bias and the other proximity effect are not necessary on this spin current generation. So this is a summarized data for the several crystal plane and x, y, and z polarized spin component of the damping-like torque as a function of the phi c. Here the phi c is a relative angle between the upright current direction and the specific crystal orientation. So interestingly, we found in the ruthenium oxide 101 case, as shown red, so we found anisotropic behavior and further unconventional x and the z polarized spin component. So here let's focus on the 101 case. So as for the y polarized components, the background corresponds to the spin Hall, conventional spin Hall effect. On the other hand, so anisotropic contribution is coming from the spin splitter effect. The further the X and the G polarized component should be from the spin splitter effect. So this is a summarized table for the conversion efficiency. We surprisingly observes the spin splitter effect is comparable to the conventional spin Hall effect from this study. So here let's discuss the crystal plane dependence, because we could not see the spin splitter effect in case of the ruthenium oxide 100 and 001. So as for the 100 case, so the prepared film has a little bit larger resistivity, around 180 micron centimeter. So this leads to the larger scattering rate gamma, around about 30 milli-electron volt. According to the theoretical report, in the spin splitter effect, the T odd spin conductivity is related to the much related to the this gamma. So the large gamma lead to the eliminating the spin splitter effect. So in this case, we could not see the effect. On the other hand, as for the 001, the resistivity seems to be okay. It's comparable to the 101 case. So therefore, at this moment, we are not sure for the detail, but maybe this is related to the spin symmetry in this configuration, because this is just a crystal structure with magnetic moments. So maybe the spin symmetry should be related to the negligible spin splitter effect, but we are not sure now. So I want to discuss this point with a theoretician after this talk. So anyway, we found G polarized spin current from the ruthenium oxide via the spin splitter effect. This is quite advantage on the field-free switching, as I mentioned in the introduction part. So this is a comparison with the conventional spin Hall effect. So as for the origin, the spin Hall effect is from the anomalous velocity driven by the Berry curvature. So this is a relativistic effect. On the other hand, spin splitter effect is originating from the spin split band structure driven by the altermagnetism. So the many presenters emphasize that this is just a non-relativistic effect. So this is very important. The further the spin polarization of the generated spin current can depend on the Near vector direction. So this is also important, because we can we are free from the orthogonal relationship like a spin Hall effect. So therefore, the spin current generated from the ruthenium dioxide could solve the switching problem. So this motivated us field-free switching experiment in this kind of the structure. So we prepared the ruthenium dioxide 101, the ruthenium and the cobalt and the platinum heterostructure. Here the platinum stands for the getting the perpendicular magnetic anisotropy in the cobalt layer. So furthermore, we already confirmed the spin current from the platinum layer does not contribute to the switching, because the platinum layer is very thin compared with the ruthenium oxide. This is just a result. So this is anomalous Hall resistance of the cobalt layer as a function of the applied charge current density. So we successfully we achieved the field-free switching in the cobalt layer. Furthermore, we found memoristic behavior due to the multi-domain structure in the cobalt layer. In order to this result coming from the spin current generation in the ruthenium oxide, we also try to perform whole loop shift measurement to extract the effective perpendicular field. This is just results with a different applied charge current amplitude. So this is summarized data. So the effective perpendicular field as a function of the applied current then we found a linearity to ensure the effective field. So with field-free magnetization switching was successfully demonstrated using the Z-polarized spin current driven by the spin splitter effect. So as for the future plan, we will focus on the magnetic domain in the ruthenium oxide. According to the theory, the theoreticians predicted the spin splitter angle should be much larger, around over the 30%. That today the Doctors Medical reported. On the other hand, as for the experiments, our group and the Ralph group, both group reported a very small spin splitter angle below the 1%. So there is a big difference. So to enlarge the spin splitter angle, we have to perform the investigation of the magnetic domain size and the reduction of the domain in the ruthenium oxide. As for the investigation, we have a schedule to do the XMLD measurements in the spring 8 in this fiscal year. So this is a spring 8 in Hyogo Prefecture in Japan. Another future plan, we are also interested in the TMR using the altermagnetism. So there are several theoretical reports for the TMR. Especially the TMR ratio is theoretically predicted to be over the 100%. So we are working on this kind of topic. So now we are trying to prepare the epitaxial heterostructure as shown here as a first trial. And for the Néel vector switching, yeah, as the professor as Son explained, we have to do the Néel vector switching in the reference layer. So in the ruthenium dioxide, maybe in ultrasyn layer, maybe we can control a little bit easily compared with the thick ruthenium dioxide. So now we are preparing the ultrasyn ruthenium dioxide onto this kind of heterostructure. So finally, I'd like to summarize my talk. The first epitaxial ruthenium dioxide as an altermagnet has been successfully prepared by means of the sputtering. The next unconventional spin currents have been generated via the spin splitter effect driven by the altermagnetism. Finally, field-free switching in an adjacent ferromagnetic layer has been demonstrated using the Z-polarized spin current via the spin splitter effect. So if you are interested in this study, so please refer to our paper published in the PRL. So that's all. Thank you for your attention.